All right, Dijkstra's algorithm. It's a shortest path algorithm. We're going to have a start node. In this case, we're going to start out at node A. We're going to look for results. The results, I'm going to make this a map. Key value pairs. So for example, if I have, I can reach node Z with a cost of 7, and I can reach node, X with a cost of 9, that means from the start node A, that's my cost to get to Z is 7, and to get to X is going to be 9. Let me go ahead and erase those. Right, so that's what the results are going to look like. Now, the way this algorithm works is we also have a priority queue. And the priority queue stores paths, not edges. So, there might be 17 links in the path to get somewhere. It's whatever the total cost of all those edges are, because we're looking for the shortest cost path from A to every other node in the graph. And so for the priority queue, I'm not going to resort it every time. I'm just going to draw it, and then we're going to visually scan through it, from top to bottom, and figure out what the cheapest thing is, and then we'll pull it out. So that's not how a priority queue actually works, but that's how we're going to go ahead and do it. So the way the algorithm is going to start, I'm starting at A, so that means I can reach node A with a cost of 0 in my priority queue. So I'm going to sort of this is my sort of configuration details. I'm going to go ahead and, what does this do? Well, you can't really see what I'm pointing at, so that's fine. What does this do? Oh, wow, that's neat. Learning how this tool works is, oh, here we go. Oh, this is just the pointing tool, so you can see me wiggle things around. That's not real helpful. Anyway, so we're starting our algorithm out. So from A, I actually have several edges. I can reach D with a cost of 2. I can reach B with a cost of 3. I can reach G with a cost of 25. And I can reach C with a cost of 10. And I may end up having to kind of scroll down to finish this graph, but that's kind of a good start. Wow, my handwriting is poor. Can I fix this a little bit? This was supposed to be D. That looks better. This is theoretically a B. So what happens? Well, I put this into my priority queue. Well, first I'm like, okay, I can reach A with a cost of 0. Great. A with a cost of 0, because A is not already in here. So A is solved. This one's now done. In fact, I could even erase it just to get rid of it. Now, I put these other things in here. For now, I'm just going to put them in order. D with 2, B with 3, C with 10, and G with good old 25. Right, so I know I can do that. Now, that's the end of the first loop. We come back up to the top. We pop the first thing out of the priority queue. Remember, it's a priority queue. The priorities are here, right? These are the priorities. So what's going to come out? D with a cost of 2. D's not already in here, so that means I can reach D with a cost of 2. Great. This one's now been solved. I can go ahead and erase it. Now we need to look at all of D's edges. And I quickly have run out of space for this. Suppose D, well, actually in my graph I'm looking at, D doesn't have any edges. So we're done. There's nothing else to do. We get back to the top of the loop. We pull the first thing out, which is going to be B. I can reach B with a cost of 3. So I can take this out of the priority queue. That is now done as well. Now I have to process B's edges. Well, what edges does B have? Well, let's suppose B only has one edge, which I'm going to actually scroll down a little bit here. I think you can still see this. Let's suppose B can get to E with a cost of 5. Now, what goes in the priority queue? Well, this edge from B to E has a cost of 5, but the total cost to E from A is actually 8. The cost to B here, right, plus the cost of this direct edge 5 down here. So what goes in here, I can reach E with a cost of 8. And suppose that's the only, well, and technically B has another edge. It has this edge here, this edge of 3 back to A. But again, I'm not going to mess with that edge because over here, A already solved. Don't need to do it again. Boom. Good. So we put that in. We go ahead and run the algorithm. We pop out the top node. the lowest cost node here, which is E with a cost of 8. Okay, perfect. I can reach E with a... That's a terrible looking E. Let's try to... You can tell why I was drawn to computing when I in the 80s, because, you know, my handwriting is so poor. So that's actually what drew me in. I want to be able to type papers. So E with a cost of 8, that's done. So we've now discovered the lowest cost to E. Now, what edges does E have? Well, let's suppose that... Oh, wait, that's not good. Here we go. Let's turn the pen back on. Let's suppose E has an edge to F with a cost of 3. Well, now, what's the cost to F? Well, it's the cost to E, which was 8, plus the cost to F, which is 3. So what goes in here, 8 plus 3, 11. We can now reach F with a cost of 11. And again, I realize that C with 10 is going to come out first. We're just going to visually scan these. We're not going to rewrite the priority queue every time. Oh, crap. I almost, threw that. No, go away. There we go. Whew. Okay. That was a close one. So you can sort of look over here. You're like, huh. F also has this edge back to E, but again, E was just solved, so who really cares? We're not gonna mess with that. Actually, that's not an issue. Oh, no, don't do that. Don't do that. There we go. It would be that E has an edge back to B, but B's already been solved, so we're not going to mess with that. Okay, good. So we run the algorithm, get to the top of the loop, we pull out C with a cost of 10. C hasn't been solved, so now I know I can reach C with a cost of 10. That's this one over here. Good. So I can go ahead and erase that. That one's gone. And now I need to look at C's edges. Now, what edges does C have? Well, C actually has 2 edges. You can see I'm working with this graph. This has a cost of 1, C to G, and C also has a cost down here to F with a cost of 2. So what goes into priority queue? Well, I can get to G with a cost of 11. The 10 it would take me to get to C plus the 1 from C to G. So I got G in here with 11. Now you can see, really cool feature of Dijkstra's algorithm, we have G in there twice. We have discovered 2 different paths to get to G. But that makes sense. There are multiple paths for getting to node G in the graph from A, right? I have a direct edge, and I have this more circuitous route. That is completely fine. Graphs are like that. That's not a problem. And then also we can get from C to F. What's the total cost there? Well, it's actually 12. We have to put that in. F with a cost of 12. And so now when we run the algorithm, what's going to come out? Well, it's either going to be F with 11 or G with 11. It actually doesn't matter which. And I don't quite know or remember how a priority queue would do this, and it may not really matter. Let's just assume it's G. So let's suppose G with a cost of 11 comes out next. What does that mean? Well, that means I've now solved G with a cost of 11. Good. Now I need to look at G's edges. Well, G doesn't have any edges I haven't already seen. G has an edge to A, but A is already solved. And then G has this edge back to, C, but C's already solved. So we don't get any new edges from G. That's all we have. So that's fine. And then, so we don't actually add anything to the priority queue. And then we keep running. What comes out next? Well, F with a cost of 11. That's what's going to come out next. So down here, we're going to have F with a cost of 11. Perfect. Now, and that, again, is going to be 3 plus 5 plus 3. That's our cost of 11. There's another edge with 12, but that's more expensive. So that's why it comes out first. F with 11, that's in there. Does F any more edges? No, it actually doesn't. And so at this point, we're actually done. We still have some things in the priority queue because we put this in there initially because that's the best path we saw, but then we discovered a better path. We also have this in here, but it's a priority queue, so we always pull out the lowest cost. And again, the cost or the priorities, we're just using sort of the total edge weights. So if we count up the nodes in our graph, there's 1, 2, 3, 4, 5. Oh, you can't really see me touching these. 6, 7. And then if you look at this result over here, 1, 2, 3, 4, 5, 6, 7. Good. We would actually be done. Once our result map is equal to the size of the number of nodes over here, we're done. Now, if we kept running the algorithm, because maybe, I don't know, there was some node down here, W, and there were no edges to W, right? So, in other words, the result map was 11, but we had 12 things. Well, we'd keep running it. We'd pull this stuff out, but we would notice that actually over here, you know, we already have a result. This is a greedy algorithm, but it's provably optimal as long as there's no negative edge weights. So the first time you find a path to something in the priority queue, whatever goes in here, that's going to be the best thing that you're going to find. You're not going to find anything better. We can do like a quick sketch of the proof of that. It's not like a difficult proof, but the intuition is if there's some cheaper way to get there, I already would have followed it because I'm always following, like what comes out of the priority queue is the thing that I can reach most cheaply at that given moment. So any lower cost path has to use other lower cost paths to get there. So I will already have found it. It's not possible that I put something in this result queue over here in my result map and then discover something better later. I actually can't do that. That wouldn't work as long as there's no negative edge weights. If there are negative edge weights, then all sorts of weird things happen. So Dijkstra's algorithm, they typically decide no negative edge weights. So this is, and then again, pretend, this isn't the thing. That was just an example. So that's Dijkstra's algorithm. I can send you this graph as well as a PDF, this graph over here. But that's what I've got. Thank you very much.